So for number 32, a child tosses a tennis ball into the air and it lands in the mud. The function that we're going to be using is h of t equals negative 16t squared plus 16t plus 4 gives the ball's height in feet with respect to time. So h of t here is like the height, whereas t represents the time. So to start here, sketch a graph of y equals h of t and highlight the portion of the curve that fits this situation. So a couple of things here reminding you how to graph a quadratic. So first of all, this is a negative quadratic. A quadratic is one of those parabola-like things. Since we're facing downwards, or since it's negative, it's going to be pointing down, which makes sense, right? Because like when we throw a ball into the air, right, it starts by going up and then it gets to the highest point and then it comes back down and it lands in our mud. So when we're dealing with that, right, that's kind of the process it's going to go through. A couple of specific things about this sketch that are important, though, is that at time is equal to 0. So I'm going to skip down really quick just to talk about this table. When time is 0, well, we should figure out what the height is. So if I were to plug in 0 into that equation, I can find out what the height is. And if I plug in 0, this is all going to cancel out because 0 times anything is 0. This is going to cancel out because 0 times anything is 0. And the height is going to be at 4 feet. So what that means is that at a time equals 0, my height is at 4. Now, again, I know this is just a sketch, but I'm really just kind of showing you where it should definitely start here. And then again, we're throwing it, and then it gets to the highest point, and then it comes back down, and it lands in the mud, which is the ground, right? So the equation that is up here that I am erasing and showing you again is a parabola that looks like this. But when it says, okay, we sketched the curve, now highlight the portion of the curve that fits the situation. Well, in this case here, really we start at 0 seconds, and then when it hits the ground, like it's not going through the ground, it's stopping in the mud. So everything that I just highlighted here in kind of like this light blue, that's the actual graph that we're going to be dealing with, the piece of the graph we'll deal with. Now, the second piece here, what's happening to the height of the tennis ball with respect to time? Well, a couple of things, right? Because once we throw it up in the air, it's starting by getting higher. It's going up, and then it gets to this point here at the top, and then it starts to come back down. So it starts by increasing in height, and then it decreases as time goes on. The next thing it says, since the velocity, which is another word for speed, is a function of distance traveled over time, what part of the graph represents the velocity of the ball? Now, this is going to be super important here and a really standard thing that we're going to deal with for calculus in general as we go forward. So what's happening to the velocity of the tennis ball with respect to time? To start, right, we're throwing it up in the air, right? So we throw it with some sort of speed, and then at a certain point, it's going to have a speed of 0 because at its highest point, the ball is no longer going up in the air. It basically kind of like stops and hovers at this point. That's this point up here at the top. So at first, we throw it into the air and it has some sort of speed. And as it gets closer to the top, it's slowing down. So when we're looking at this, as time goes forward, it's starting to slow down as it goes up. And then it begins to speed up from that point on as we're going down. Now, the important thing here is that what part of the graph represents the velocity? Well, that is going to be the slope, because again, we're saying it is distance traveled over time. So in this case here, the slope at any point, let's say at this point right here, this slope, that's the speed at which it is going. And again, it's always changing, right? It's always slowing down. So it's not always that same slope here, but really the velocity is the slope of this graph. That's kind of a key thing to remember. Next, copy and complete the table to the right of time S versus height F of t. So when we're going through this, really, I'm not going to spend a bunch of time on this because I think that you can plug in some numbers, but really what we're doing here is, I'll rewrite this, is h of t equals negative 16t squared plus 16t plus 4. So there's my equation, and really all that you should be doing throughout this is plugging in these times in for t and solving the equation. So plug those in and get those values. I'm not going to spend the time in the video to do it. I'm just going to go ahead and start writing the answers. So once we go through and we plug in the numbers and we keep getting those answers, if you plug in 1.5, if you actually do the calculations, you'll end up getting a negative number, which doesn't actually make sense in this situation, because remember when we talked about highlighting which part of the graph was important, well, we highlighted this blue part, and at this point right here, that's at 1.25 seconds. So 1.5 seconds, well, it doesn't go below the ground. So really, technically, this is still 0, because after another quarter of a second, the ball hasn't gone through the mud. It's just still sitting there. So that's just a kind of a technicality just to pay attention to. So the next thing it's asking us to do is use the table to determine the ball's average velocity in feet per second for each quarter second time interval. So if we're dealing with the slope, key thing here, the slope, remember, is the change in y, so y2 minus 1 over x2 minus x1. So when I say velocity is equal to the slope, remember that's really just the rate of change. So a better term to use here would be the rate of change. Now again, this is fairly math intensive, so I'll do the first one just so you can see the process. But when I look at the velocity over this time period right here, I'm going to take the y values, which are 7 minus 4, over the x values, which is 0.25 minus 0, and that gives me 3 over 0.25, and then I divide those, which gives me 12. And again, you can use a calculator on this. But really, I'm going to go ahead and kind of add another piece to this table here. So this right here, the speed between this time interval is going to be 12 feet per second. So what you're going to do is you're going to go through and you do that for each of them, right? So the next one would be 8 minus 7 over 0.25, and so on as you go through. Note that at certain points, you're going to end up getting negative numbers. If you get negative numbers, that's a good thing, because we know that the velocity starts to go down, which would be the negative speed. To go through and you actually get those numbers calculated, then you should get 12 feet per second for the first, then 4 feet per second, then negative 4 feet per second, negative 12 feet, negative 16 feet per second. Last thing it's asking us to do here is to predict the velocity of the ball at 0.8 seconds. So 0.8 seconds is in between these two spots right here. Let me do this in purple so it highlights a little bit better. In between these two pieces. So I know that the speed over that whole time, or the velocity, is going to be negative 12, but when we're at 0.75 seconds, it's not going that fast yet. So I'm going to say it's actually going to be between these two numbers. So I don't know, we could say, you could do a little bit more math intensive stuff, or I'm just going to kind of estimate if it's between negative 4 and negative 12, I'm going to say it's going to be about, this is for F, about negative 8-ish feet per second. And again, that's just kind of an estimation. The key thing to understand here as you're going through this problem is that the speed is the velocity is kind of the rate of change when we're dealing with distance over time graph.